All right, well, that's perfectly timed by my clock. So I'm gonna get started. Hi everyone, welcome to Lab 7. Yeah. Um, could someone mute themselves? I think I'm like hearing feedback. Um, this lab is going over simple linear regression. We're gonna use try a bunch of methods to fit a simple linear model. So let's start. We're gonna try 5 different methods to fit linear model. So let's start by running our configuration cell and loading in our data. We're gonna be using the same TIPS data set we used in last lab. It's a classic Seaborn, or like this is used in a lot of data science libraries. It's a data set on TIPS and the bills and the people paying the bills. Great. So last lab, we fit a constant model to this data set, meaning we fit a model that predicted the same value regardless of any of the details on the sale. And we fit this model by minimizing the risk. And remember, the risk is the expected loss on any randomly selected point from the data set. But we don't know we don't have access to the full population, so we don't know the expected value on any value. Instead, we use the empirical risk, which is the average loss on all the points in the data set to estimate the true risk, or like the model risk. So here, we also looked at 2 different loss functions. We looked at L2 loss, which involves the squared error, and we looked at L1, which is the which is the absolute error. Now, in this lab, we're gonna fit a model with 2 predicting using the bill. So we're gonna have to fit 2 parameters rather than 1. We're gonna fit an intercept term and a coefficient for this total bill variable. And yeah, and the optimal values we call A hat and B hat. So the first method we'll look at is LM plot. Seaborn has this function LM plot. It plots a scatter plot of the 2 variables, and it also visualizes the least squares regression line between the 2 variables. Now this is really simple and does it automatically, but let's start with question 1, where we're gonna manually fit this. So in lecture 14, they Serge went over how to obtain the least squares estimates for the intercept and slope. And they did this by using calculus to minimize the squared error and solving. But and if you want to review, check the lecture 14 notes. But the results we got were some form of this. Well, now this equation is actually slightly, I guess, like reformulated from like the traditional like A plus BX we're used to. Yeah, this is the and so for 1A, we're gonna plug in we're gonna plug in the values for these constants in the model to obtain so that we have a function that can output predictions. So let's start with filling in X bar. Here, X is our predictor, and in this case, it's our total bill. So for X, we just need the mean of the total bill column, and I think our data set is called total TIPS. Similarly for Y bar, we just need the mean of the variable we're trying to predict, which is TIP, the TIP column of our TIPS data set. Standard deviation X, we're using, it gives, and in the hint, it gives warning, use np.std, not series dot standard deviation. It has to do with they calculate it slightly differently, Panda series. And so yeah, we're just plugging in the values for these constants. And then For the correlation coefficient, the hint tells us to use mp dot core coef. So let's see what that is. We can also look up um, how to doc for that, but it takes in two arguments. One is the one variable, an array of one of the variables, and the other is the other variable. Let's look at what that gives us. And so this and numpy core coef returns a matrix, but we only want a single value. We just want the correlation coefficient between the two variables. And we can do this by subsetting this matrix to one of these values. If we think about what this correlation matrix represents, this first entry is the correlation between tips and tips, then tips and total bill and tips, and total bill and total bill. Notice that the correlation between tips and tips, or the same variable, is 1 because it's the same variable. So the value we want is just we just need to subset this to the to this first row, first row, first column, or the second row, first column, to get this correlation coefficient. And that should pass. Great. And now we want to set we'll find b hat and a hat in terms of the variables we define above. Hint, try to match the slope and intercept in y equals a plus bx to the slope and intercept in this reformulated equation. Well, if we for b hat, let's start with b hat. We know b is just the slope, which is it's just whatever is the slope. It's whatever is multiplying x by. Like if we look at the form of this original equation, it's constant plus slope times variable. And here we have constant plus constant times variable minus constant times constant. So to extract the slope, we just need to find the slope is just whatever is multiplying the variable, which in this case is r times sdy, and I think we called that stdx, or no, stday divided by stdx. Yeah, and then for the intercept, well, it's just the constant parts of this equation. We can so here we have constant plus this is something of variable, but then minus this constant times constant. So we can extract this using the constant. We can just the constant is just equal to all the constant parts in this, which would be y bar minus this value here, which we determined was actually b hat, times x bar. Great. So now we've manually computed some estimates for the intercept and slope, and we can use them to predict the tip amount for a given input. So, for example, 20. So, if we want to predict the tip for a bill of 20, we could use a hat, the intercept, plus the slope times the input, which was 20. And that is about $3.02. Now we want to do this not just for one value, but for all the values of all the total bill values in the data set. And luckily, Python allows vectorized operations, or like if we can just substitute in for this single integer 20, we can just substitute in an array of values, and it will perform the operation as it does for a single one. So what I mean by this is we just substitute in the array or the column total bill. Regression should return an array of values with this operations applied to all of them. And it does. Great. Make sure that was correct. And if you define regression correctly, the following cell will generate a scatter plot of tip versus total bill along with the line of best fit. So let's see if our manual computations got a similar plot to Seaborn. And the scale, like the axis scales are off, or like the range is different, but this looks about the same. Now let's consider the correlation coefficient between tips and total bill we found. R equals 0.67. It's asking us to comment on the value of R and what it means in the context of the above scatter plot. Well, the correlation coefficient, it ranges from -1 to 1. 1 or -1 means it's, highly correlated. 0 means uncorrelated. And I'd say 0.67 pretty highly correlated, and we can see that in that the positive slope is related to the or it's like, yeah, is proportional to the correlation coefficient. And yeah, so that's I guess the slope has significant, looks like, I guess the slope is greater than 0. I don't know. No, it doesn't. All comments are valid here. Not. Okay, let's just say not. That's terrible. Okay. Well, for question 2, let's transition to question 2, which is we're going to use SciPy minimize to solve for the intercept and slope. So SciPy minimize is a powerful method from the SciPy package, and it can find the values that minimize a function. It's very powerful, but it's a little overkill for this application, but still useful to know how it works. So let's use the L2 tip. Let's use this function to minimize this L2 tip risk. When we say L2, it's using the L2 loss function, and it's finding the empirical risk, which is the average of the average value of the loss function across the entire data set. So our first step is to create this function L2 tip risk, which returns the L2 loss between the regression line for the L2 loss for the regression line with this intercept and slope. So let's make our predict. So if we have this intercept and slope, our predictions are, well, it'll give us the input A, and we'll use that intercept plus the slope times. And since we're using the tips data set, we're X and Y here are just going to refer to the total. X will be the total bill column of the tips data set, and Y is the tip column. And then if we want to return the L2 loss, the L2 risk, it's the mean squared error, which we can calculate using np.mean on the squared error between the and Y here is the tips. These are values minus our predictions. And then we square this difference. Be really careful about parentheses here. It's a common mistake to get confused here. You want set of parentheses for the np.mean surrounding the square difference, and make sure that these are in parentheses. I've just seen a lot of errors where this it goes wrong. And yeah, I think I did that right. And so now let's use our function to find the risk for different A and B values. See if we use values close we tried earlier in this lab, we can see it's lower. And so this minimize function can minimize functions with multiple variables, but there's one requirement, and that is that the function has to accept its parameters as a single list. It has to the function can only take one argument, but that argument can be a list with containing multiple parameters. So for example, if we were to use minimize to minimize this function f of u and v, we would need to use minimize on it. We would need to translate this function to a function of one variable, but then we could just extract these other like the, I guess, parameters in a list where theta is a list. So then if we, and then once you have it in this form, you can run scipy minimize on it. I noticed this extra argument x naught. X naught specifies the initial guess for the optimal theta. Minimize works by like, it starts with an initial guess, finds the value of the function at that guess, and then it adjusts towards the minimum. And does this iteratively. We'll talk about how, like this process, like with gradient descent and other, I don't know, optimization functions, but yeah. So, but yeah, like a common initial guess is 0, 0. That's just a standard initial input. So now we're going to want to translate our L2 tip risk function into a function that will work with this scipy minimize function. So this is we're just going to program it the same way, but instead of taking in two, instead of taking in like A and B, we're going to extract A and B from this list they pass in. And so now we have A and B, we can just do the same steps as before. Predictions are A plus B times tips at Bill to the X values. And then we return the mean squared prediction error. Great. So now let's use now that we have our function in the correct form, let's use minimize to find the optimal parameter. So we're minimizing our L2 tip risk list, and let's specify our initial, set our initial guess. Pretty sure you could see anything here. I'm just gonna do 0, 0. It's pretty standard. Let's see if that worked. Let's look at our output. This first one here gives us the value of the function at the minima, and this last value here gives us the values of the parameters that minimize this function. And notice those are pretty close to what we had before. Yeah, like we had like 0.9. I can't find it, but yeah, I mean, those, yeah, I'm pretty sure those are all very close to what we had before. Oh yeah, they compare it right here. So yeah, these are very similar to what we got manually, but after like 5 digits, 5 decimal places, they start to get I guess like disagree, but that is just due to the fact that scipy minimize is a numerical method. Meaning it approximates the optimal value using non-algebraic procedures. So, but they're basically for our purposes they're basically the same. So now let's try and do that same approach, fitting an intercept and slope and an optimal optimizing this, but instead use scikit-learn. Scikit-learn is a really powerful machine learning for Python. The way way you generally like initialize it is you from scikit-learn, one of the packages in it, you import some object, which in our case we're importing a linear regression object. Then we initialize this model here using this syntax, linear regression, parentheses. And here model is now like a blank slate. It knows that it needs to fit a linear model. It just doesn't know, but you need to tell it, tell it which data to fit to. And also note when you pass in the predictor data to fit to, that needs to be a matrix. And so if you were to just pass in the tips the total bill column, that would error. Yeah, it would error because it needs the predictor values to be in like 2-dimensional or matrix form. And you can do this by passing in the column name as a list, and that will subset the to the total bill column as a data frame. And now that you fit the model, you can look at its attributes. You can look at its coefficients. This would be its, I guess, its slope. You can also look at the intercept it fit, and then you can also run predict to predict different values. And you pass in the predictions. Once again, they have to be in like matrix or some two-dimensional form. And it gets the same prediction we had for when the total bill is 20. Great. So for 3A, create a linear regression plot using model.predict. It should look the same, if not very similar as the one for 1D. So we're just going to make another scatter plot with the regression line running through it. So let's get our predictions. I'll call them fitted now. Just fitted is the same word as prediction, same meaning as predictions. So we're going to want to predict, use our model to predict all the to make predictions for each of the total bill or the total bill values in the tips data set. So now fitted is this array of predicted values. Now we want to make a plot. Let's first, to make it similar to the 1D, let's use let's first scatter. I'm going to use Seaborn to scatter the data. Let's make first, I think we had total bill, the x-axis. We have tips, and let's just see what that looked. Oh, you're angry. Let's see. Oh, right. Total bill has to be in a matrix. They got me. And now you're angry because total bill y equals tip. Oh, I think it's supposed to be tip. Values. I'm not using the right. I think I need to do data equals tips. Okay. Yeah, I think the issue there, I think what I had before, I didn't specify that equals. I think it assumed that when I put the tips value in here, I was doing it like positionally. It assumes that would be like the x value, so it didn't. If I'm gonna put in the arguments out of order, you need to specify the argument. So yeah, I could put it in that order too. It would work. And now we want to plot our regression line. I'm just going to use basic matplotlib plot function. We want our x values are the tips at total bill, same as for the scatter plot. And then our y values, we want to plot the predictions, and I'll just make that red so that we can see them. And predictions, I probably spelled that wrong. Oh, fitted, I called it fitted, my bad. Great, and yeah, that looks almost the same. I think, yeah, pretty much identical to what we had for 1D. Has anyone had any difficulties with the lab so far, or any questions on what we've done? Let me know. Otherwise, I'm going to transition over to Alex. Great. Alex, are you there?
Yeah. Can you hear me?
Yeah. Here.
Cool.
Are you able to share it? Okay. I think it's enabled.
Yeah, I think so. Let's see here. Cool.
Great.
Can you see my screen?
Yep.
Great. Let me pull up the chat here so I have this. All right. Howdy, y'all. We're going to be going over some multiple linear regression. So if you have any questions, feel free to speak up or put it in the chat. I'll try to get to, I'll check the chat every now and then. Okay, cool. So we're going to be going over multiple linear regression. So this is going to be very similar to what we just did. It's just a further extension. So rather than having something like of the form y equals mx plus b, we're going to have multiple independent variables. So in the description here, and in this class, we're going to be using features, independent variables, and explanatory variables interchangeably. So this is going to be the case where we have more than one x value for a specific single data point. In this example, there's p of them. So we have x1, x2, all the way through xp. And as usual, we still have our intercept term, which is this theta naught. So in other words, we're going to be given some data, and the data is the x values themselves. So we're given x, and we want to try to find the theta values that help us accurately predict what y is going to be. So in this, for the rest of the lab, we're going to be using a new data set. So we're going to use the Seaborn package, and we're going to load the data set MPG, so miles per gallon. And this has a lot of really cool data pertaining to different types of cars. So over here, we can see like this is a Volkswagen 1131 Deluxe sedan, and it has a bunch of information about the car. So the cylinders, the displacement, horsepower, weight, acceleration, model year, and origin. So these are like our X values over here, these columns. And then we want to try to predict what the miles per gallon is going to be based on all of, based on those specific columns, or maybe a subset of them. So going back to this equation here, this yi would be miles per gallon, and then we could view these x columns or these x variables as the other columns over here. Does anyone have any questions on that? So I know it's a little weird because normally when you think of linear regression, it's just with one variable against another response variable. So it's like two variables in total, an x and a y. So here we're going to have multiple x for a single y. This has to do with like higher dimensional data, which is common in the real world. It's a little harder to visualize conceptually because we can't really visualize things above 3 dimensions, but we can try to describe them as best we can. Okay, so we'll just run these first few cells to load in our data. This just gives us a view of what it looks like. We can go ahead and plot. So for these questions, we're going to be mainly concerned with horsepower first against miles per gallon. So here we've plotted horsepower on the x and our response variable miles per gallon on the y. So we can kind of see here that there seems to be some downward trend, and it seems slightly curved. So we can go ahead and try to plot this line against them. Clearly, a linear line doesn't quite get the job done as well as we want it to. To further see that a linear line might not be the best fit, the best model to fit against this data, we can plot the residuals. So this is going to be our residual plot. So we can imagine a line across the 0 here. And we can see a clear trend. It seems to start up here in the 15, dip down below 0 to negative values. And then as we go across the x-axis here, we kind of swoop back up. So there's a clear trend in our residual plot. Those of you who took AP Stat might remember that our residual plot ideally would look random across the entire range of data. Here, there's a clear trend. So that's an indicator that we can do something with our data to hopefully get a better model that better fits our data, right? So that's what this cell is kind of explaining here. This is not an example of a good residual plot. There's a parabolic pattern in the residuals, so we want to consider adding quadratic features. So that's what we're going to do here. So clearly, horsepower itself alone left a clear trend. So we're going to try something out here. We're going to try to add a horsepower squared. So this is exactly just going to be our original horsepower column, but then we're just going to square it. So we've added another feature. So this is an example of interpolation. So we're taking some existing data that we've already had, and then we're going to change it in some way to create a new feature. So over here, we have horsepower squared. This is somewhat similar to this scikit-learn function, or article, I should say, of polynomial interpolation. We're basically generating new data from existing data to hopefully see if we can get a better fit. This isn't super important that you know the nuances of this, but just in case anyone's curious, this is what we're kind of like attempting to model. So we're just going to square one of our features, and then that's where we jump into question 4a. So we're asked to, now using this new feature in conjunction with our old one, can we try to fit a linear model to this? So we're going to have this new linear regression model. We'll call it model multiple. So the syntax is going to be very similar to before. We can just fit this, but now our x values that we're going to use to fit this model are actually two separate columns. So we can do vehicle data. And then our first column is going to be horsepower. So we can view this as X1. And then our X2 data is going to be this horsepower squared column. Our Y is just going to be our miles per gallon that we wanted to predict before. So we can do vehicle data and miles per gallon. Cool. So that should give you this output line, linear regression, and some other debug output along with that. We can check the auto grader. Okay, that's weird. 1 second. Let me rerun these lines. One second. Why is that not running? I just ran the cell. Okay, 1 second. Let me restart my notebook. Oops, sorry. Okay, we'll rerun this. All this stuff. And then we'll run, oops, sorry. We'll run this import statement, and then let's try this again. Okay, it's really weird. I have an extra bracket somewhere. Okay, that might be, yeah, give me 1 second. Let me see here. Okay, let me actually just copy this line, make sure it's right. Ah, there we go. Yeah. Okay. Small typo. Thank you. Okay, so we should be here now. Is everyone good up to this point? So we've just fitted this linear model. So now we're asked to view the coefficients of this model as well as our intercept. So what these represent are those theta values that we've looked at earlier. So if we scroll back up to the very start of this question, so question 4, we have this theta 0, theta 1, and theta 2. So that's kind of what we're looking at. So our coefficients themselves are going to be the theta 1 and theta 2, whereas our intercept is going to be theta naught. So question 4b asks us, using the above rules in LaTeX, please write out the function using to predict the miles per gallon from horsepower and horsepower squared. So I'll go ahead and add this in here. So right now I've just written this out as intercept plus coefficient 1 times horsepower plus coefficient 2 times horsepower squared. So now we can actually fill in those values. So our intercept, we can see the output here was like this 56.9, it looks like, rounding off. Our first coefficient is going to be this negative 0.46, negative 0.466. And our coefficient 2 is going to be this 0.00123. Right, so let me get rid of that plus. There we go. So we have something that looks like this. So our miles per gallon is predicted to be 56.9 minus 0.466 times the horsepower of whatever car we're looking at, plus 0.00123 of the horsepower squared. So it looks like horsepower itself at first has kind of a negative impact on the miles per gallon, but as our horsepower gets higher and higher, it has a stronger effect, indicated by the positive 0.00123 coefficient. So we can go ahead and plot our new regression model. And we can see something that looks like this. So this is a bit better of a model than before. It looks like we fit along the curve with more of our data, especially with these higher values. So we can go back to before and kind of compare that. So it looks like with the linear model, so with the just one straight line, it looks like as we get it to horsepower of 225, the line is pretty far off from our actual data. So now with using the horsepower squared, it looks like we can kind of fit to that higher end data a little better, right? Does anyone have any questions up to this point? Cool. Okay, so 4C. So in this cell below, explain why the term linear is used to describe the model above, even though it incorporates horsepower squared as a feature. Okay, so this is a concept where the polynomial interpolation comes into play. So even though some of our data itself is squared, we're still linear in the features themselves. So in other words, if we were just given the horsepower squared already, we're not doing anything differently than we did before with compared to the linear model, right? So in other words, we know from before that this is how a linear model is represented. So we have one response variable y is equal to scalar multiples of our input data. So that's where this theta 1 through theta p multiplied by x1 through xp comes into play, along with an intercept term. So now specifically with the example that we're looking at, we can just limit it to the first two variables. So we have theta naught plus theta 1 times x1 plus theta 2 times x2. So we know that this is linear in terms of x. So now let's just take it one step further and say, okay, what if I told you that x2 is actually x1, but it's squared, right? So in the second line, we said that this is linear already. So just by defining x2 as x1 squared, that doesn't necessarily change the essence of the actual equation itself, right? It's still linear in terms of x1 and x2, which is exactly the features that we've been given. It's just now we know something a little more nuanced about what x2 actually is. It just really happens to be the square of x1, but still, if we view this in terms of x1 and x2, it's still linear, right? So that's why this model is still considered a linear regression model. We've played around with the input data so that way we can view something that maybe in real life isn't linear, but we fit it into a linear kind of like composition, right? So we don't have to make our model any more complex than it already is. All we did was we tweaked the input before we made our model, right? Does that kind of make sense? Does anyone have any questions about that? So the question itself, why is the model above still linear? So I've written out our model right here. Well, it's linear because the inputs themselves, we're just trying to find the same scalar values for them. In other words, we're linear with respect to our inputs. Okay. So if there are no questions there, so now we're going to be looking at just the r squared values. So there's nothing to do for this question. It's already done for us. We can just kind of talk about what this means. So if we looked at the model with just using horsepower, it looks like our r squared value is 0.605. And if we look at our model using horsepower and horsepower squared, r squared goes up to 0.68. And we're asked to think about what this means with respect to our refined model. So typically the way that we can view this is as r squared increases, we can view this as an increase in strength of the representational strength of our model. In other words, how well does our model fit to the data that we've been presented? And this is kind of an indicator of how strong or weak our model is at doing that. So typically, and I say typically because you can overfit, which we'll see soon, but typically a higher r squared value means you have higher representational strength, which is typically better. Okay, so question 4D. So in the cell below, we assign the mean of the MPG column of the vehicle data frame to mean MPG. Given this information, what is the mean of the predicted MPG and the predicted MPG of using horsepower only? So it turns out that the real mean, so this first row here is the real mean, and then these two following rows are going to be predicted mean. predicted mean. We're asked to figure out what these means are, and we're asked to do it without calling np.mean. So it turns out that all three of these are actually the same. So this happens to be a kind of like one of the features of using a linear regression model. This happens to be one of the inherent properties of the linear regression model, specifically when we have an intercept term. So this is a link to the lecture 13 slides. I'll link it really quick in chat in case anyone wants to check it out. It should be slide 40 and 41. So it's also right here. So these are properties when our model has an intercept term. And what we're looking at right here is the average true y value is equal to the average predicted y value. And this follows from the property that the sum of the residuals is always 0. So I won't talk about this too much because this is actually a question in the homework to prove this, but this is a good place to get started. So this is all in lecture. If you haven't seen the most recent lecture yet, I encourage you to check this out before you attempt the homework or go through this problem. But this just happens to be one of the inherent properties. So this question is just a matter of plugging in mean MPG for both of these lines. Right, and then we can run the autograder just to confirm that. So you'll prove that in homework. Okay, any questions so far? All right. So question 5. So for question 4, we just use 2 columns. We use horsepower and horsepower squared. So now we're gonna take this another step up and we're gonna use 4 columns. So this would be like using x1, x2, x3, and x4, as well as an intercept term. So we can go ahead and do that. So our desired columns, what are they gonna be? So this is just gonna be a list, and we're told that we want the horsepower column. We want the horsepower squared. We want the model year. Typically, we would expect that a more recent model year probably has a better rating for miles per gallon. Acceleration, typically a higher acceleration is probably an indicator of lower miles per gallon. Physics and whatnot. So let's give that a go. And autograder says we're good to go. So now let's go ahead and plot what we're seeing here. Cool. So this is definitely a more accurate model than we saw before, but it comes at a price. So kind of what this next cell is talking about is it's really jagged. Do you think that this is good to predict the miles per gallon of a new car that we haven't seen yet? And this is the idea of bias variance trade-off. So here our model is much more specific. It's better representative of the data that we've received. But at the same time, like all of these jagged lines make it really difficult to kind of say, okay, what if we were given a new car that has a horsepower of 80, right? On this graph, well, it looks like these jagged lines are so close together, we could really kind of predict this. Let me zoom in here, really anywhere in this range, right? So this is the idea of really high variance. So our model is much more accurate, which is the term of low bias. So we have lower bias here, which means our model represents our given data pretty well, but it's got really high variance. So we can see here that we're jumping around a lot. And if we go back to our graph from earlier, when we just had horsepower and horsepower squared, we can see here that this simple curve right here is maybe a lot better at predicting. So we have a lot lower variance along this line. And if we fitted this across different sets of this data, but it's got higher bias in the sense that it's more difficult to kind of predict these values that are out, almost like outliers or out of the range of this predicted line here. So this is a common term in data science and also machine learning called the bias variance trade-off. So that's what this cell is talking about here. We'll explore it more in the coming weeks, so it's not super important to know about it very specifically right now, but this is going to be kind of like one of the big talking points of the models that we're seeing in this class. Okay, cool. So now on to 5b. So lastly, set R too many is to be the multiple R squared coefficient obtained by using model many. So like the earlier model with just horsepower and horsepower squared, we want to view what this R squared value is. So we can go ahead and take a look at that. So where was it? Up here, we did this. We took this code here. Oops, sorry. Where did I go? Yeah, so it's this NP variance. So we can kind of copy this down here below, and then we can fix our inputs. So now we're going to do predicted miles per gallon many. And then we want to divide it by the variance of our output data. So let's go ahead and check that. And we can see here all three of the models that we've looked at so far. So predicting with only horsepower, we get an R squared value of 0.605. From earlier, when we used horsepower and horsepower squared, we got 0.68, so a bit better of representational power. And then now using all four of these columns, we get an R squared value of 0.8163. So we can see here that our representational power went up a good bit. So this is what I was talking about with this line fits a lot of our data a lot better, even though it's very jagged. Cool. So yeah, so that's what we're talking about here. So we might not always want to use models with large R squared values because these models could be overfitting to the training data. So that's what, again, what we're seeing here. We're really overfitting to a lot of these particular values, whereas we might want to settle for something with a lower R squared value for something more generalizable. So we'll see that more as we get into more of these machine learning methods. So yeah, that's the last question on this lab, and we've got 3 minutes to spare. So does anyone have any other questions or concerns about what's going on here before we kind of bring it to a close? Anytime. Cool. Stephanie, do you have anything left you want to say? Cool. All right. I guess we're pretty much good to go, guys. And as always, if you have any other questions, feel free to post on Piazza.